Good evening, everyone, and welcome back to our series of presentations from the Kavli Institute for Particle Astrophysics and Cosmology at Stanford University, as we invite you to join us to discover our universe. Wherever you're joining us from tonight, we hope that you're safe and healthy. My name's Dan Wilkins, and I'm a research scientist at kipac, and I am the coordinator of our public talk series. You can find out all about our events over on our website, kipac.stanford.edu/discover. There you can find details about all of our upcoming talks, and over on our YouTube channel, you can watch any of our past talks again. That's all linked from the website. Well, tonight, we're joined by Senior Staff Scientist from the SLAC National Accelerator Laboratory, Dr. Phil Marshall. He's going to tell us all about the new ways we'll be able to discover the universe using the Vera C Rubin Observatory that's currently under construction in Chile. Now, Phil is an observational cosmologist who uses the deflection of light as it passes by massive objects to weigh galaxies and to measure the expansion of our universe. He's the Deputy Director of Operations for the Rubin Observatory's Legacy Survey of Space and Time, and he works with a team of scientists to make sure that that observatory is going to successfully deliver the data that we need to learn all about cosmology and dark energy. He got his PhD from the University of Cambridge, and that's where he first got interested in measuring astronomical objects, especially those that we can't see directly. And Phil, first of all, came to Stanford in 2003 as one of the first postdocs when kipac was founded. He then spent 3 years at the University of California, Santa Barbara, 3 years back at Stanford, then 3 years as a Royal Society University Research Fellow in Oxford, UK, before finally coming back to the Bay Area to join the permanent staff at SLAC. So we're very lucky to have Phil here tonight. Now, we'll be hosting a Q&A session with Phil after his presentation. So if you have any questions, you can send them in to us at any time. If you're joining us on Zoom, head down to the bottom of the screen and hit the Q&A button, and you can send your questions in there. And if you're over on YouTube, just send in your questions through the chat. But for now, I'll hand over to Phil.
Thanks very much, Dan, and good evening, everyone out there. Thanks for spending your Tuesday evening with us. It's good to have you. Okay, I'm going to go ahead and share my screen so you can see some slides with me. Let's see. Okay, let's do. Okay, so exploring the universe with the Vera C Rubin Observatory. It's a pleasure to tell you about this fantastic new facility. I've been working on this for quite some time now. I started on it when I was first at Stanford back in 2004. And it's been a very interesting project to work on, still is. And it's led to me thinking about science in some new and interesting ways. And in fact, when I met my now wife, she was asking me what I do for a living, and I was explaining about Rubin Observatory, LSST as it was then, and what we were doing with it, and why. I was explaining that we have these big questions in cosmology. Where did we come from? How does the universe work? What else is out there? And that we were doing it not for profit or for improving technology, although that does happen, but we do it because we're just interested, and we think everyone else is. And then I sort of waxed lyrical for a bit longer about exploring and so on. And she said, "Oh, you're like Magellan." So that got me thinking, I mean, are we really like Magellan? It turns out it's a pretty good analogy, exploring the universe with giant telescopes. It's not a great analogy, and I'll explain why towards the end of the talk. But let's take a look to get started at what Magellan actually did. What made Melinda think that what I was doing was like anything like Magellan, what Magellan was doing? So Ferdinand Magellan, he in 1517, he proposed a westward voyage to the Spice Islands. This is what explorers do. They imagine new things, write a proposal, get prepared, and then boldly go. So he took off in 1519 with 273 crew and 5 ships. Only one of those ships came back, Victoria, with only 18 men on it, and Magellan wasn't one of them. So in this conversation with Melinda, I was trying to explain that I was hoping that by the end of the LSST survey, there'd be more of us left over than there were in Magellan's expedition. But anyway, Magellan started out, when he wrote his proposal, presumably, his big question one is there a way to reach the Philippines by sailing west? That was what he was interested in. And so off they went, and were pretty successful, as I'm sure you know. So here's the main result from Magellan's exploration, his voyage of discovery. When they got back to Europe, Diogo Ribeiro took all the data that he'd collected on the ship and made a map. And the map turned out to be extremely important. They found a small, narrow strait between two land masses at the very tip of South America that you could sail through. And when you went through the Straits of Magellan, as they're now called, the whole of the Pacific Ocean opened up. And they set off across it, an enormous distance, and eventually reached the Philippines, the Spice Islands that Ferdinand Magellan was trying to get to. So these Straits of Magellan, they opened a route to the Pacific and beyond, and showed this whole ocean of possibility with a path forward that we didn't know was there. So this is what explorers do. But what possessed Magellan to go off on this expedition in the first place? Well, here's an interesting quote by the man himself that I think gives some insight into his thought processes. He wrote, "The sea is dangerous and its storms are terrible, but these obstacles have never been sufficient reason to remain ashore. Unlike the mediocre, intrepid spirits seek victory over those things that seem impossible. It is with an iron will that they embark on the most daring of all endeavors." He was a product of his time, Magellan, back when machismo was still cool. But this last part is the most important, I think. He wanted to meet the shadowy future without fear and conquer the unknown. So I think what Magellan was most interested in was the things that he didn't understand. He wanted to find out more. He wanted to open up these oceans of possibility. And I think that's what he and modern day scientists have in common. So what do voyages of discovery look like in the 21st century? Well, to get started on that, here's a nice quote from Marcel Proust. "The real voyage of discovery consists not in seeking new landscapes, but in having new eyes." So here's a new eye on the sky at Rubin Observatory. We're building at SLAC the biggest digital camera in the world. It's going to be suspended above an 8.5 meter diameter mirror, feeding a data facility that will process 500 petabytes of data. This is an amazing adventure. Just if you're interested, 500 petabytes of data is, well, the disks that you would have to buy to store that. You could also store a copy of every book ever published in every language currently in use. A huge amount of data, and we'll come back to that later. It's important. So this will be, telescope will be based in Chile. That's where the observatory is. The data facility will be in the US and France. Headquarters is in Tucson, and the National Lab hosting the construction of the camera and the cosmology that's being done with this, that I'll get into a bit later. That's happening at SLAC. Okay, so let's see how we're getting on building this fantastic new facility. Here's a picture of the summit facility and dome as it was in February 2020. You can see in this aerial view a giant crane that's was being used to lift the telescope mount assembly into the dome. And you can see the dome was partially closed up with panels on, so beginning to really take shape as an observatory. Here's a cross-section through the summit facility. You can see on the left here, there's our telescope in its dome. You can also see next to it, there's a giant elevator that we'll be using to take the mirror off for cleaning and resurfacing from time to time. And then there's this hall, experimental hall for fixing things, resurfacing the mirror, as I say. And the control room is actually as far away from the telescope as you can get, down in the bottom right-hand corner. So this is this facility is partway built. It's in use, and I'll show you what's in there happening. So a little bit about the telescope. This is the Charles Simonyi Survey Telescope, named for the entrepreneur who donated the money to get us started building the mirror. The telescope weighs 300 tons, but can slew 90 degrees in just 9 seconds. So that's doesn't seem like much, but for a 300-ton structure, it's actually pretty fast. Let me show you what 90 degrees of slew looks like in 9 seconds. It's from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So easy for me to do slowly, but when it's a giant telescope, that's pretty quick. It's quick on purpose. We're a survey telescope. We're trying to survey a lot of sky in a short amount of time. So we'll take a deep 20 gigabytes image every 40 seconds on average. So you can see our disk drives are going to fill up pretty quickly. So if I take away the mount assembly and just look at the optics of this telescope, we use 3 mirrors to form an image that is both wide field of view and low distortion. And it's an unusual design for a telescope. We used to call it the large, short, stubby telescope for fun. The tertiary mirror, that's the third one that the light bounces off, is actually ground out of the middle of the primary mirror in order to make everything work. So to show you what's going on, look at this little picture down at the right-hand side. You've got light coming in from the night sky, bouncing off the primary mirror, which is this outer annulus of the big mirror, up onto a secondary mirror, and then down for a third reflection in the middle part of the primary. That's the tertiary, and then the light gets reflected back into the camera, which has some corrective lenses and then a filter, and then into the detector. I'll show you more about that camera in a minute. It's the size of a car suspended above this 8 meter mirror. So all the screws need to be put in tight. Here you are in the mirror lab in Tucson, Arizona. This is when we were building the mirror, and you can see what I mean about grinding out the tertiary from the primary. There's me, young me, in 2008, 1 year into the fabrication of the mirror. The mirror is called M1, M3 because it's the primary and the tertiary together. And it took 7 years to build. It's a big piece of equipment. It's surprisingly complicated for a mirror, not just a mirror. So that mirror was finished, put in storage for a while, and then when the Summit facility was ready, we shipped it up there in 2019. Here's a photo of the mirror in its box being hauled up the mountain in Chile, and you can see it just makes it through the tunnel at the dam by design, and we can then see it going up the mountain. This is Cerro Pachon, the mountain in Chile where the observatory is. If you look closely, you can see a silver dome up there. That's Gemini South, if you're familiar with big telescopes. And there you can see M1, M3 being pulled up the mountainside. Okay, so I mentioned this camera, and I told you that it was being built at SLAC. It's true. And the top right-hand corner, you see a room called IR2. It's actually in one of the old experimental halls up at SLAC that used to host the Babar experiment, if you're familiar with that. So now we have a clean room where we're putting together this giant camera. Here you can see suspended just a piece of the body of the camera, looking down as it will be in real life. And on the left-hand side, you can see inside that camera body, you can see the focal plane. This is where the sensors are, the silicon chips that detect the light, CCDs that detect the light. So since January, the sensors have all been installed and the system is being tested. Things are going well. You see a cutaway view of this giant camera on the right-hand side. Look how big the filters are. We take black and white images, but through colored filters. We have 6 different color filters, and from that we can form a color composite image. The filters are huge, so 0.5 meter across. So very excitingly, today we released our first image from LST camera. That's the name of the camera. And this is the world's largest digital photograph. And here you see it on the left. That's a Romanesco broccoli seen through a pinhole by the LST camera. And I'll explain what the grid lines are all about in a second. But on the right, you can see how we did it. There's the focal plane looking down at the top. And then we have a light box with a broccoli Romanesco head inside. So this was taken by the LST camera team at SLAC. Many of our colleagues at kipac are pretty excited about this. So let's dig into this giant image since we have it now. This focal plane is actually made up of 21 rafts. It's a modular design, so we can take out rafts and put them back in when servicing the camera. And if we zoom in on just one raft, you can see it's made of 9 sensors. those sensors, if we zoom in further onto one of them, then you can perhaps see that it's made up of 16 rectangular amplifiers. Those are those faint lines on the far right-hand side image. So just a single sensor, a single square, as it looks in the image on the left, is itself a 19 megapixel digital camera. So this is a huge camera. And I showed you the zoom because that's really the benefit of the LSST camera. It's a very wide field for this type of astronomy. But it has a huge number of pixels, which means we can zoom in a long way. In fact, so far, that if you were 15 miles above the Earth's surface, pointing LSST cam down, you could resolve a golf ball on a green. Okay, we'll come back to that in a second when I show you what it will look like on the sky. So we were on schedule for first light in 2021 and starting the survey in 2022, but then the pandemic arrived and put a stop to everything, as you've noticed. The summit's currently closed and winter is coming, so the construction project's going to be resetting its schedule this fall. And in the operations team where I work, we're expecting delays of 6 to 12 months, and we're planning for a year. So we'll get there in the end. Here's the crew. I told you that Magellan had 273 crew. Here's our crew. We have hundreds of people working on the construction project and getting ready to operate the facility. Those are the people all wearing identical blue t-shirts on the left. Yeah, we always dress the same. It's one of those things. On the right, you can see the LSST Dark Energy Science Collaboration. That's the big team of cosmologists from all over the world that will be using the data from Rubin Observatory to do cosmology. And I'll tell you a bit more about in a minute. But this kind of project, this is big science, takes hundreds of people to get it right. Okay, so why do the pieces of Rubin Observatory look the way they do? We have this big, short, stubby telescope, and we have this giant camera with a big field of view. It's all about surveying the night sky fast. So what does that look like? Well, our plan is to spend an entire decade, 10 years, imaging the whole of the southern sky. So that's 18,000 square degrees, possibly a bit more, and we'll complete the imaging of the whole of the southern sky, at least the part that's visible at that time of year. We'll complete that every few nights on average, and then go back and do it again and again and again. And we'll do that for 10 years. And at the end of 10 years, we'll have built up something like an 825 frame movie in 6-filter Technicolor. And it turns out you can do an awful lot of science of lots of different types of astronomy with that one data set. And so we named it the Legacy Survey of Space and Time, which was cunningly chosen so we could keep the same acronym that we had before, LSST. So let's look in a bit more detail about the survey images in the LSST. This is a big data project. The field of view that I showed you on the focal plane and the camera at 60,000 pixels across. What does that mean in terms of zoom? Well, you saw the illustration with the golf ball. You can also think of it in the following way. To print out just one of these LSST images at standard printer resolution, 72 dots per inch, you would need a 70 by 70 foot piece of paper and 3 tennis courts to lay it out on. So it's all about the zoom, being able to look at well-resolved astronomical objects in large numbers at the same time. So if you look closely in the top right-hand corner, there's the full moon. That's how big the full moon would be relative to the LSST camera's field of view. If we now just zoom in on that little patch of sky that has the full moon in it, here's what it looks like at something like LSST resolution. This is actually a real image of the sky from a different survey called the Canada, France, Hawaii Telescope Legacy Survey, which has properties similar to what we expect from the LSST data, but it won't have the repeated imaging over 10 years, or it doesn't have that. And it's taken over a much smaller patch of sky. But nevertheless, the images look somewhat similar to the ones we're expecting. So here's what the night sky looks like behind the full moon when you have a big telescope and you're taking long exposures. If we zoom in a little bit more, first to get back our frame of reference, there's a human hair held up at arm's length. if we zoom in, there's that hair again, and then just next to it you see quite an interesting object. That's a group of galaxies, a group of red galaxies that's acting as a gravitational lens. There's a faint blue galaxy in the background, and the light from that faint galaxy is being bent as it comes around the massive object, and you end up seeing multiple images of the same blue source. So this is a gravitational lens. It's what I do my cosmology research on in my when I'm not deputy directing operations. I think they're fascinating objects, and it turns out they're quite useful for cosmology. So I'll show you more about that in a minute. Okay, so huge amounts of sky being surveyed, billions of objects with trillions of measurements. That's what we're in the business of doing with Rubin Observatory. The data facilities will automatically process all this imaging and measure every object's position, brightness, size, and shape. So all the stars, all the galaxies, every time we image them. So then we'll put all of that into a giant database. We call it the catalog, but it's a database. You can see a sort of one representation of a tiny piece of it in the bottom right-hand corner. And we'll make that catalog available to thousands of astronomers in the US, but also elsewhere around the world, to analyze those automatic measurements and start comparing them to predictions from physical models. And then we'll be doing science with LSST. Okay, so what kind of astronomy will we be able to do with this testing data set? So we'll start close and then move further out, okay? So the first thing we'll be able to do is we'll be able to make a really good census of the solar system. The LSST survey images will contain something like 5 million main belt asteroids, 300,000 Trojans, they're the asteroids that are in Jupiter's orbit, 100,000 near-Earth objects, they're the ones that we really, really want to know about, especially when they're coming at us fast, and 40,000 Kuiper belt objects in the outer regions of the solar system. And we'll detect all of these as moving objects. Remember, we're taking multiple images, successive frames will contain the same objects, just appearing to move across the sky. And we'll be able to put together their orbits in that way. What could we do with this census of the solar system? Well, one thing is we already know that the spins and orientations and walls of the planets in the solar system, they're not as simple as you might expect. Neither are the orbits of the Kuiper belt objects that we know about. And it turns out that one simple way to explain all this unusualness compared to simple models is to make the model a bit more complicated by adding an extra planet. Not one that we can see today, but one that must have been there, so the model goes, in the distant past. Somewhere around out where Jupiter was, a planet about the size of Neptune, planet 9, that has been kicked out by gravitational slingshot effects from the solar system so that we don't see it anymore. And on its way out, it caused a lot of wobbling and shifting of spins and things. So these models predict that there's a long lost detectable planet called planet 9. It's somewhere out in the Kuiper belt. And this is the kind of thing that the LSST images could contain. So we'll be going out looking for planet 9 with Rubin. Here's an ocean of possibility for you. Because we're taking successive images over the course of 10 years, we'll be able to explore the time domain. We'll be able to explore how things in the night sky vary in time. We'll be able to watch the stars flickering in brightness. We'll be able to watch stars exploding as supernovae. And in fact, this graph on the left shows all the different kinds of exploding transient events that we know about in the universe and where they appear in terms of their intrinsic brightness, that's the axis going up, and the duration of the explosion going to the right from 1 day to 3 months. And you can see in the top left-hand corner of this plot, there's a big empty space where we don't know much. It turns out to be quite hard to catch things going off with short duration. You have to get lucky, or you have to make yourself lucky by doing a big sky survey like the LSST. So we hope to learn something about, for example, what happens when black holes collide by having the ability to survey the sky repeatedly very fast. Okay, so remember back to the main result from Magellan's exploration. It was a map, turns out. Rubin will also be making maps. We'll be turning the LSST data into maps. So what are maps? Well, they're simplified representations of data. On the left here, you see a satellite image of the Bay Area. That's not a map, that's data. The map is the thing that you pull up on Google that uses that data to show you where everything is in a simplified and hence useful way. So maps are good for us. They reveal paths forward that we might not have realized were there. For example, how to get through the traffic in the Bay Area quickly rather than slowly. So what kind of maps can we make with the LSST data? Well, here's one. We can make maps of where the stars are in our own galaxy. So on the right here, you can see a map of stars in the Milky Way Galaxy. This was made with the Sloan survey, which is one of the precursors to the LSST. And you can see here lots of stars in the Milky Way. You can see streams of stars going across the sky. And it's actually quite a bit more complicated when you look in detail than you might have thought for our galaxy. With the LSST data, we'll be able to make a better version of this map. We'll be able to go further out in distance into the Milky Way. We'll be able to detect more streams of stars. Because whenever you look deeper in astronomy, you see more stuff. That's what the two images on the bottom left are showing. And there's a lot of interesting things going on in the outskirts of galaxies, it turns out. So why are we interested in the outskirts of galaxies? Well, we've been interested in this ever since the 70s. So here's Vera Rubin in 1975. She got interested in the stars in the outer parts of galaxies and how fast they were moving. She was an excellent spectroscopist. She took spectroscopic data of stars and used that to measure their speeds, their apparent speeds going away from her or coming towards her. And she did that for stars towards the center of galaxies, like M31 here, that's our neighbor galaxy, Andromeda. She measured the speeds close to the center, and then she stepped out in distance further and further away from the center of M31 and kept measuring the speeds of stars. And she found that they were high speed, but they were still out there. So what does that mean? Often when things are moving at high speed, it's hard to keep them in. If they're moving at high speed and they haven't escaped, that means something is holding them in. And the only thing we know in the universe that holds stars in galaxies is gravity. And so she was able to work out how heavy, how strong the gravitational field was of M31. And it turned out to be such that M31 is quite a bit heavier than it looks. And this led her to propose that actually there was a lot of mass in M31 in the form of dark matter. So we can go study this with the LSST data. Here are those streams of stars I mentioned, illustrated down at the bottom right, but seen in the Sloan star map on the left-hand side. Now look at the picture on the top right. You see there's a stream of stars. This is from a simulation of a galaxy. You see that stream of stars and it's got a little kink in it. We expect those kinks in streams to form when they get cut across by something heavy like a dwarf galaxy that's in orbit around the Milky Way. So the picture down the bottom right shows what happens when one of these dwarf galaxies is in orbit around the Milky Way. It leaves a stream of stars behind it, and a stream of stars gets pulled off the front as well. And then when another dwarf galaxy cuts across that stream, you get a little kink. And because the kink is caused by gravity of the passing satellite, you get one of these kinks even if the satellite galaxy doing the cutting doesn't have any stars in itself. So little blobs of dark matter in the outskirts of our Milky Way will cause kinks in streams, which means if we go out and we find a lot of kinks and study them, model them, we can figure out how many little clumps of dark matter there are in our own halo. And from that, learn something about what the dark matter is. That's the hope. Okay. So Vera Rubin, remarkable lady. Here she is on the floor, the observatory floor, I think at Carnegie Observatories down in Southern California. I like the look on her face very much here. And it goes well with a quote she's famous for. There is no problem in science that can be solved by a man that cannot be solved by a woman. And speaking to the men out there, you've probably might have fallen into the trap once or twice of thinking that only a man could do a job. Well, here's Vera Rubin looking straight at us, reminding that it's probably not true. Okay, more sky maps. With the LSST data, we'll be able to map out the positions, brightnesses, colors, and shapes of several billion galaxies. Here's a simulation of what that map might look like. You can see that galaxies are arranged in clusters and groups. That makes sense, right? Because they, over the history of the universe, we expect things to fall together by gravity. So groups form and then groups fall together to make clusters, and you end up with this kind of structure on the sky. So by mapping out where the galaxies are, we can figure out what the underlying structure of dark matter might be. So this simulation was made by a computer model of dark matter and galaxies into a virtual box, and then letting physics take its course. And now that we see that the map of galaxies in this prediction for what the map of galaxies will look like with LSST, we can ask, well, what does the dark matter underneath actually look like? And here it is. It has this marvelous filamentary structure between the clusters and groups and galaxies that our best models for what dark matter is predict. And so we can go out and we can try and trace those filamentary structures, the clustering of galaxies, and we can try and do that by looking at their gravitational effects. These clusters, these groups, these filaments should be causing slight distortions in the images of galaxies behind all of that cosmic web. And that weak gravitational lensing effect will allow us to map out where the dark matter is, as well as where the galaxies are that we see. So I think this is really cool. Here's a picture on the right of light from a background blue galaxy passing through the universe. As the universe evolves from left to right, structure gets more clumpy as gravity acts, and we should be able to reconstruct how clumpy the universe was, how this filamentary structure was forming at different times in the past by looking further and further back and making weak lensing maps at different epochs in the universe's history. We'll be able to see how the structure in the universe grew. This is a fantastic opportunity for cosmic archaeology. So why am I interested in this as a cosmologist? Well, here's our model, current understanding for how the universe is expanding. On the left, at the beginning of time, we imagine there being a big bang. It's good evidence for that, caused the microwave background. And then after that, for about 400 million years, darkness, not a lot going on. Gravity pulled together enough gas to make stars, and those stars clustered into galaxies, and from then on, there were interesting things for optical astronomers like me to look at. But look at this picture. Something interesting happens within the last few billion years. You might expect the expansion of the universe to slow down as gravity acts and pulls the galaxies back together. And you might expect everything to be slowing down, the expansion to be slowing under the universe's own weight. It turns out that's not what's happening. Turns out that the expansion of the universe is accelerating these days. And no one knows why. It's a bit like having spent a whole life being told that what goes up must come down. And then one day you find when it comes to the whole universe, it's not true. So this is the biggest mystery in physics right now. Why is the expansion of the universe accelerating? So theorists like this one will be thinking of models, ideas for why the universe is expanding at an accelerating rate. While they do that, the observational cosmologists like me, our job is to try and make the most accurate measurements of that acceleration that we can. So that when, as the theorists come up with ideas for what might be going on, we can test those ideas and start ruling them out. That's what the theorists want. They want their ideas to be ruled out. It's true. And then the idea is at the end, we'll be left with the idea that works the best, and we'll call that our current understanding. So we're in the business of making accurate measurements of acceleration in the universe. How do we do that? So measuring acceleration, imagine a car accelerating down a hill, rolling down a hill, getting faster and faster. Its acceleration down the hill depends on how steep that hill is. So to measure the acceleration of that rolling car, one thing you can do is you can time it down the slope, and then you can figure out how steep the slope was and figure out how fast the car was accelerating. Turns out you can do something else as well. You can look at the car coming down the hill, like in this picture of San Francisco, and try and figure out what the steepness of the hill, what the grade of the hill is, just by looking at it. And maybe you can imagine that, looking at these cars, all their headlights are roughly the same brightness, but some of them are further away than others. And you could maybe just about go along with me that you could estimate how steep this hill was just by looking at the cars coming down it and how bright their headlights are. Seems like a tortured way to measure acceleration, but it turns out to be really useful in the universe. One of the ways we can measure distance in the universe, we can measure the accelerated expansion fairly directly, is by looking at the brightness of so-called standard candles, things where we know the intrinsic luminosity, or we think we do, and then we can use that to measure distance in the universe and compare it to the apparent recession speed of that object. So standard candles useful for measuring cosmic acceleration, and we're going to find a lot of them with Rubin. So several thousand new supernovae detected every night is what we're looking at. A very large sample of type 1a supernovae, these special supernovae that always look the same. And those standardizable candles are the ones that we can use to measure distance. Why is it important to have huge numbers of these? Well, if you have 100,000 supernovae, you can divide them up into groups. And you can say, okay, I'm going to measure the accelerating expansion of the universe in this direction on the sky. And I'm going to compare it with the acceleration rate that I see from all those supernovae in this direction on the sky, and say something about whether the universe is expanding in the same way, that way, compared to that way. So this is something that hasn't really been able to be done before, but we'll have enough data with LSST to be able to do that. Okay, turns out we can measure distance in other ways, and I want to spend a few slides on this. This is from my own research with research group I work at kipac. And it's interesting, I think, because it illustrates how the enormous LSST dataset makes us think differently. Okay, so I said gravitational lenses can allow you to do cosmology. They provide a way of measuring distance in the universe. These multiple images of background objects, like you see in the picture on the top left-hand corner, you can imagine if those bright white background objects are flickering, changing in brightness with time, well, you could imagine that the light that goes one way around the massive lens galaxy arrives at a different time than the light that comes around the other side of this massive lens galaxy. And the delay between those two signals, between those two flickerings, is what we can use to measure distance in the universe. It's not quite the distance to the lens galaxy or the distance to the source galaxy, it's some combination, but that's okay. It's enough to be a physical distance that we can measure. And we can use that to probe the acceleration. So LSST, this survey will provide measured time delays for hundreds of these lens systems. And it'll also provide information about the massive galaxies that tend to do this kind of lensing for thousands more. So this is a big sample that we can put together. The thing is that to do accurate cosmology, to be able to measure distances to each of these lens systems, you need a very good model for where the dark matter is in these galaxies, for where the stars are and where the dark matter is. And only if you have a good model can you calibrate the lens and actually use it to measure distance. It turns out right now that to do accurate lens modeling is very time consuming. It takes several weeks per lens to measure the parameters of the lens and the distance to the lens and estimate their uncertainties. So what are we going to do when we get to analyze hundreds of these systems? So at SLAC, we've been using AI, thinking differently and using AI to do super fast lens modeling. Get this, several weeks per lens down to a few minutes per lens is the goal. So what we do is we use deep learning networks similar to those used in facial recognition, but we don't have our robots spend their time looking at faces. We have them looking at model lenses. So we teach them what model lenses look like. So when they see a real lens, they say like that what they think it is in terms of a model lens. So we make millions of these synthetic lenses where we know the true parameters, and then we show the trained network a real lens and ask it, what's the model, what's the distance? And this is going pretty well. How well we can actually take this industrial technology and have it cope with our astronomical uncertainties, that's our research question. So far, so good. The results are promising. We're still in sort of moderately idealized conditions, but we think we can do accurate cosmology with competitive precision about 10,000 times faster than current modeling methods. And I don't think we'd be focusing on this if we weren't getting ready to cope with our own personal big data problem, which is the LST survey. All big data problems are personal, by the way, almost by definition. Amazon and Google have absolutely big data sets, but lots of people have personal big data problems. Okay, so this was work done with students Ji-Won Park and Sebastian Wagner-Carena at kipac, along with Simon Vera and Aaron Rubin, all up at SLAC. Oh, I must apologize to my director. Risa Wexler is part of this group as well. I'll fix that for next time, Risa. Okay, so I spent some time trying to persuade you that Rubin Observatory is a bit like Magellans Ship. You know, it enables these voyages of discovery. We'll make maps just like Diogo Ribeiro did. But it is different than Magellan's exploration in one very important way, which is that when Magellan wrote his proposal, he was motivated by, exploring the unknown, but he was funded by the King of Spain. And it was clear to everybody that the benefits of his explorations were going to fall to the Spanish. And it turns out at the expense of large numbers of people in the Americas. So Rubin is different. Our maps, our data set, they're intended to be for everyone. So here's a picture of what is really our ship where we go on voyages of discovery. It's that little pale blue dot there, the boat that we're all on together. So what does it mean for Rubin data to be for everyone? Well, we'll provide many different maps for other explorers to follow, and that certainly includes you. And we'll be trying to actually make it possible to explore the universe with Rubin to as many people as we can. The data set will go public, and we'll be actively building tools to help people like you across the world explore the universe with Rubin. So how is this going to work? So we're partnering with the Zooniverse to enable citizen science. This is one way we can give everyone a chance to explore. So I'm one of the PIs of this project, Space Warps. I'm not sure if we have data in at the moment, but spacewarps.org is worth checking out sometime. It's a citizen science project where we enable anybody to come and help us estimate, judge whether something that we've seen in a sky survey is a gravitational lens or not. So here are some examples of, here's an object that might be a gravitational lens. And we ask the collective neural network of thousands of volunteers what they think, and they turn out to be pretty good at finding lenses, especially the complicated ones that we didn't put in our synthetic training set when training the AI system. So citizen science will be a chance for everyone to explore the Rubin data. Actually teaming up with the Zooniverse, they've built a project builder, which will make it relatively easy for scientists like me to put together projects for lots of us to do together. Could be classification of objects, could be making measurements together. What I'm really hoping, though, is that we see citizen scientists who are not professional scientists as well, but are coming up with their own ideas for exploring the universe, and then partnering with professionals who have time and funding to do this kind of thing with them to build projects and go explore together. So that's an interesting idea, right? What does it take to be a scientist? You might be out there thinking, could I be a scientist? I think you already are a scientist, but what does it take to be a scientist? Let's ask Vera. Here she is in the 1940s as an undergraduate at Vassar College. And on the left, I've written out an interesting anecdote for you from her childhood. She tells the story of how she had a bedroom as a child, and where the bed was under the windows that faced north. And when she was about 10, while lying in bed, she started watching the stars just move across the sky. By about 12, she says, she'd prefer to stay up and watch the stars than go to sleep. So this motivated her. She started learning, going to the library and reading. And she said that there was just nothing as interesting as watching the stars every night. She found it a remarkable thing. You could tell the time by the stars. She would memorize where each meteor went, each shooting star, so that in the morning she could make a map of their trails. So this was Vera, age 12, being a scientist. She goes on to say that even then, I was more interested in the question than in the answer. I decided at an early age that we inhabit a very curious world. So I think there are two things it takes to be a scientist. The first thing is you just need to be curious about how the universe works, how the world works. The other thing I think you need to be a scientist is the willingness to not ever give up. And Vera was good at that too. Okay, so as well as citizen science, we'll be doing other things to get the LSST data into the hands of as many people as we can. We're especially interested in helping children get their hands on it, because children make excellent scientists. They're very curious and they don't give up, and they come up with all sorts of interesting ideas. So we'll be working with children across the world in the classroom, providing things for them to help them learn about astronomy, how it works, and help them think about the universe and have their own ideas about it. So here are some examples of things that we'll be giving out to teachers to work with in the classroom. We'll also make it possible to give everyone a sense of the adventure. This is the LST Sky Viewer. You may have seen the Sloan Digital Sky Survey Sky Viewer. This will be similar, but because of the time domain aspect, because of the higher resolution, there'll be just a whole lot more to see. We'll try and give it some more advanced features as well, and make it really interesting for people to go out and explore the universe using this web-based tool. So I hope that's inspired you a bit to find out more about Rubin Observatory and get excited about the survey starting in the next few years. I'll leave you with one last quote from Vera Rubin. So she wrote towards the end of her life, the joy and fun of understanding the universe we bequeath to our grandchildren and to their grandchildren. And she says, with over 90% of the matter in the universe still to play with, even the sky will not be the limit. Okay, thanks very much for your attention.
Okay, thank you, Phil. I'm definitely looking forward to seeing those first images and those first results from the Rubin Observatory. And I'm sure I speak for many of us when I say that Vera Rubin's words about what it takes to be a scientist really do resonate. And we've definitely had a lot of interest from our audience tonight. We've had a long stream of questions coming in. So we'll start off with the telescope itself. So you showed that impressive 8.4 meter mirror, particularly being driven all the way up the mountain and squeezing through the tunnel. What is a mirror like that made of, and what sort of facility do you need to manufacture such a thing?
Yeah, okay, so it's glass, but it's complicated. It's actually a honeycomb glass structure inside with a smooth glass panel on top. It's honeycomb to try and make it light, because a solid piece of glass would be just too heavy to work with. So it's made of glass, and then we coat it with shiny metal. We illuminize it. The second part of the question, Dan, I just blanked on it.
So what sort of facility do you need to make that mirror?
Okay, so we went past quite quickly, but the Mirror Lab in Arizona has these great big dishes that you put chunks of glass in and then heat it up. They're ovens, and it melts the glass, and then you spin the dishes very slowly at just the right rate to make the outer parts of the liquid come up against the edge of the oven and the inner parts come down. So that's the easiest way to make a parabolic mirror. And then to make the spherical mirror inside, you just have to spend a lot of time grinding it out with a drill. And so those are the things that they do at the Mirror Lab.
And if any of you are wondering where in Arizona you can hide a mirror lab that big, they actually keep it under the football field at the university.
Yep.
So on the subject of that mirror, so you showed how it had those three different mirrors, or well, two of them actually part of the same mirror. And we had a question actually come in. Why does the telescope need three mirrors instead of just one mirror and having a longer distance you can focus over?
I know, right? It does look like we've made things more complicated for ourselves than we need to. But it's because of the need to make a very good, clear image over a very wide field of view. It turns out that it's quite difficult to do that, to make very, very crisp images over a wide field. And the optics with these three mirrors and then the lenses inside, what they do is they arrange the light after all those bounces such that you end up with an image that is good at the edges as well as in the middle. That the stars and the galaxies are still well resolved and not distorted at the edge, just like they aren't in the middle. And that's why we go to all this trouble to make the light bounce around.
Yeah, and when you're trying to survey the sky and scan that over the whole sky, you don't just want an image that's good in the center, I guess. You want to make sure you can use every bit of that giant digital camera image without getting weird distortions from the mirror on it.
Exactly, because we take those images that we take and then we add them up, stack them together, we call it. And so we want all of the images to be good everywhere so that when we stack them together like this, you get left with a very deep image that is still good resolution.
Yeah. So from here on the ground, you might be forgiven for thinking when you look at the stars with the naked eye that they're all kind of close to black and white. So one question we had was, why do you need all these colored filters? What are you getting with the colors?
Good question. So let's see. The main thing you learn in astronomy from having a color image, or rather measurements of a star, for example, in different filters, you get a sense of how hot it is. So hot things tend to be bluer, you go from red hot to white hot. And the same is true of stars. And so there are differences in color of stars, and they are interesting and useful. The hotter stars tend to be bluer, and the cooler stars tend to be redder. And so we can study stars in more detail if we have color information. The same is true for galaxies. If you have a galaxy that looks blue, it's because it has a lot of young, hot, white stars in it. If you have a red galaxy, it's because those hot, massive blue white stars have all gone off pop, and you're left with the lower mass red stars that are still there. And so that tells you something about a galaxy's age, or at least when it was doing most of its star formation. Is it forming stars now? Yes, if it's blue, no, if it's not. And so we can start to understand stars and galaxies in a lot more detail if we have color.
Yeah, but there's certainly a lot more colors to see than we can with the naked eye as well.
Yeah, I didn't go into this. We do have an ultraviolet filter, and we have three near infrared filters, and then three filters in the visual range.
Okay, great. And are those pretty standard range filters? We actually had a question from an amateur astronomer who's been watching tonight. What are the filters that we're using?
They're very similar to the filters that we used for the Sloan survey. Partly so that we could make comparisons between the LSST survey images and the Sloan images. We can calibrate them against each other. There are some differences to try and make the best of the properties of the sensors, which for LSST camera are more sensitive in the infrared. And so we've designed the filters to try and make the most of that. And in particular in the Y band, which is our most infrared, our reddest filter, that has some interesting shape to it to try and avoid the bright skylines due to the water. But the U, G, R, I, and Z are the same as are commonly in use in present day surveys.
Great, well, thanks. So comparing the Rubin Observatory with, I guess, some of the other truly remarkable observatories that people are familiar with, how does the resolution and sensitivity of Rubin, how does it compare to the Hubble Space Telescope?
Right, okay, so it's true, if you go above the atmosphere, you can make higher resolution images. And so the images from the LSST survey will not be as high resolution as those from HST. So to put some numbers on it, the important thing for the resolution of an image is how wide does a star appear to be. We call it the point spread function, but you can think of it as like how blurry does a star appear to be. From space with HST, it's roughly, a star would look roughly 0.1 arc seconds across. That's how blurry it is. From the ground, the typical average image in the LSST set will have resolution that's 0.7 arc seconds, so 7 times worse than Hubble. But remember, we're taking 800 images over the course of 10 years. And the sky blurriness, the atmosphere changes from night to night. And so there'll be times when we get lucky and the sky will be really clear. And there we're expecting to get images that are resolution more like 0.5 arc seconds. So very good for ground-based astronomy, but not as high resolution as HST. The thing you get from Rubin is the volume of data. Hubble just isn't big enough. It's not a survey telescope. It's not able to survey the sky fast enough to do the kind of big data experiments and investigations that we want to do. So it's for a different purpose. I think actually what we'll end up doing is finding lots of interesting things in the LSST data and then using space telescopes to go and take a closer look.
Yeah, definitely a lot to follow up on with that. Getting those sort of broad pictures of the sky from the survey and then really zooming in on the objects of interest. And actually, as somebody who spends a lot of my time thinking about observatories that we can launch into space, we can just never launch something as big as the Vera Rubin Observatory into space. A big constraint we have on launch is the mass, just how heavy and how big the telescope is. And I mean, first it starts pushing the cost up, and then after you've pushed the cost up, it just becomes impossible. The engineering is just impossible to get something that big into space. And there's a lot we can do with these giant telescopes on the ground. So on to some of the science that we hope to be able to do with the Rubin Observatory. So you talked about scanning the sky and being able to pick up exploding stars and colliding black holes. How often do we expect to see stars exploding or black holes colliding with Rubin?
So the number I tend to remember is the one that's interesting for cosmology. So that around 1,000 or that kind of order of magnitude, 1,000 new supernovae per night. Now, there'll be a whole lot of other explosions going off that we'll also see, but those 1,000 are the ones that are useful for cosmology. So I would say it's going to be in the 10,000, 100,000 range of new transients every night. There'll also be a whole lot of stuff in our images that is confusing to our automatic measuring machine and will appear in the catalog as if it was a new transient. So part of the challenge with Rubin is filtering out the stuff that is bogus and keeping the stuff that is real. Those are technical terms, real or bogus. And so we'll need to do a lot of classification like that. And then we'll need to do further filtering so that eventually the astronomers out there waiting with their follow-up telescopes get a high quality stream of new discoveries to go follow up rather than a whole lot of noise. So that's one of our big data problems is filtering the alert stream.
Yeah, and would the Rubin Observatory interrupt its survey if it sees something very interesting, or would it be on the other observatories to follow up to get that extra look?
Oh, that reminds me, the director of operations, Bob Blum, and I regularly have this conversation. Yes, we need a TOO policy. So the idea is, yes, we will take targets of opportunity, stop the survey and do something, go and point somewhere special if there's good reason to. It turns out that there's relatively few reasons why you would ever do that, because there are other telescopes that we have that are just as good for most follow-up, but just as good or better for most follow-up purposes. The big exception to that is these gravitational wave events. And the reason they're different is because if we detect gravitational waves from a certain part of the sky with LIGO or later, we hope, LISA, It'll be very exciting, as you've already seen, but as you might already know, they're hard to locate on the sky. You don't get very good angular resolution with a gravitational wave telescope yet. And so the challenge is to go to the rough part of the sky where we know the gravitational wave signal came from and start surveying it to find out where the new transients are. So we'll have a back catalogue of Rubin detections and measurements that will give us our backdrop. If a gravitational wave event happens, we'll be able to slew over there and start doing a mini survey to look for a new and interesting transient that could be the optical counterpart of that gravitational wave event. And those are the things I think we'll stop the survey for.
And thinking about technology and how technology is likely to advance over the next few years, is the technology on the Rubin Observatory something that could be easily updated to keep it state of the art?
Yes and no. It's all in the word easily. So the conversation has started about what to do with Rubin Observatory after the first 10 years. First 10 years we will do this legacy survey of space and time. After that, it's not clear. And of course, what we do in the second 10 years kind of depends what we find in the first 10 years. So we have to stay flexible. What I think we'll do is about halfway through this decade, we won't stop surveying, but we'll take stock. We'll have a workshop. We'll get the community together and look at what we found, and pin down what we really want to do in the second survey. So what could that look like? Well, there are cheap options and there are expensive options for upgrading the LST camera, or more generally the Simone Survey Telescope. Cheap things to do include things like making new filters and getting additional color information to that we'll already have. That will improve our measurements in a number of ways and would be relatively straightforward to do. We'd keep surveying the sky. We maybe would design the way we do the survey differently the second time around, but we would still survey the sky because that's what the Simone telescope does. It's a survey telescope. Getting more expensive, we could think of taking out the CCD rafts from the focal plane and replacing with different kinds of detectors. Maybe something that's more sensitive in the infrared, or maybe speculatively something that is even more sort of color sensitive without the need for a filter. This is getting into left field a bit now, but this is the kind of conversation that we're going to be having over the next few years. The really expensive option would be to I forget the word when you're doing this on a car, but when you take a car and you turn it into an almost completely different car by replacing the engine and putting spoilers on the back and all that stuff. Yeah. If we were to do that to LST camera, I guess what we would do is try and turn it into a giant spectrograph and spend the next survey taking spectra, which is just the kind of logical extension of the more filters idea. Get more information about the colors of things, because that's really useful for understanding stars and galaxies.
Yeah, but of course, I think the most exciting things about the Rubin Observatory and any new observatory, there's the things we design it with the view to discover, but there's also the things that you have no idea you're going to discover, the serendipitous results that come out of it. And I guess once we start seeing what we can discover with such a fantastic telescope, that'll really decide which way the upgrades go.
Yeah.
So on that topic, we've just got time for one last question. Out of all of the discoveries that the Rubin Observatory could possibly make, what would you say is the one you're most looking forward to right now?
Most looking forward to? I think it's the one that gets made by a citizen scientist who came up with the idea to do the project. I think that's what I'll get most excited about, because I love the idea of the LSST dataset being for everyone.
Yeah,
I think that's what I'd be most excited about.
Yeah,
Planet 9 would be cool, but citizen-led science is even cooler.
Yeah. And with such a rich data set, there's no end to the ideas you could come up with to test from it. So we're really looking forward to that. Well, thank you so much, Phil, and thank you everyone for joining us tonight. If you would like to see Phil's presentation again, or any of our past presentations again, they're all recorded. They're over on our YouTube channel, youtube.com/kipac. But for now, we'll be back in 2 weeks, Tuesday, September 22nd, when Dr. Andrew Bradshaw from SLAC will be telling us about some of the problems that satellites can cause when they fly over our observatories and get in our images. I mean, in particular, how they're going to impact these large projects, such as the Rubin Observatory. So that's definitely an interesting topic and something that's becoming much more important with the raft of new satellites that are being launched at the moment. You can find out more about that and all of our upcoming events over on our website, kipac.stanford.edu/discover. But for now, stay safe. We'll see you again in 2 weeks. Bye-bye for now, everyone.